In this video, we will look at a problem that looks very difficult and complicated at first, but after applying a series of observation, this problem turns into a very standard problem in competitive programming, and we have a lot of tools and known data structures and algorithm to solve that problem. And not only that, in this video, we will discuss two different approaches to this problem. One is the beginner way, that is what you would ideally follow in a contest, and one is the advanced way. That is, once we have solved this problem using beginner level techniques, and once we know the final set of observations that are needed to make it to that are needed to solve the problem, I will show you how, if you are an advanced level coder, then you could have arrived at this same conclusion much faster and without so much of the casework that we are going to do. But either way, I think this is still a good exercise for you to learn how to actually solve it in a beginner fashion first. And once you do that, because see, hindsight is 2020. As soon as you see the solution via the beginner method, you will start claiming that the problem is very easy, because everything will fall in place. You will say that, okay, yes, of course this observation holds true, and of course this observation holds true, and I could have come up with it myself. But the problem is that a lot of the times you are not able to come up with these observations in a contest, because you always resort to the absolute basics, which is all right while solving a problem. But in the later parts of this video, you will also see how not to dive into the absolute basics every time you want to solve a problem, and how to approach it in a holistic way such that you can arrive at the same conclusion much faster and in a much cleaner way. So we'll see both of these approaches. Now let's talk about the problem description. So this problem appeared in a recent Codechef Starters round, and this was problem D of a diff2 round. But I would say that it is not too difficult of a problem. In fact, this uses ideas from the last Codechef Starter problem that was based on LCM. I have already created a video on it on my YouTube channel that I will also link down in the YouTube description. And in that video, if you remember, I had linked a practice problem in the YouTube description. And this problem is a straightforward application of that practice problem. So if you really solved the practice problems that I asked you to, you will see that the formula from that problem can be directly applied over here, because that formula is the standard technique that I was referring to in competitive programming. So now, with all that aside, let's talk about the problem statement. So it says that you are given two integers n and k. You are given integers n and k. These are the only two integers in your input. You are not given an array and nothing else. Now let us consider an empty array of length n, and then let us locate all the sliding window of length k. So here you can see that the length of this array is 6, and assume that k is equal to, let's say, 3. So you can see that this is the first sliding window of length 3. This is the second sliding window of length 3. This is the third sliding window of length 3. This is the fourth and the last sliding window of length 3. Then you can see that each sliding window is colored in a different color. So let us compute the maximum element of the first sliding window, which is colored in blue. So maxima of this, and this. Let us call it as B1, which is any arbitrary number B1. Then let's compute the maxima of the second sliding window, that is maximum of all the green elements. So this, and this. Let us call it as B2. Then you compute the maxima of the yellow sliding window. Let's call it as B3. And you do the same thing for white sliding window. You call it as B4. So once you have this sequence of number, and notice that there will be n minus k plus 1 sliding windows, because you can see that with 6 and 3 the formula is 6 minus 3 plus 1, because we got 4 numbers. So you have to ensure that B1 is less than B2 is less than B3 is less than B4. That is, this sliding window maxima itself should be in strictly increasing order. So your goal is to, given that your goal is to place elements from 1 to n in this array, you have to place elements from 1 up to n. Not necessarily you don't necessarily have to use all the elements, but you can only use elements in this range from 1 to n, while ensuring that whatever placement that you are doing, after doing the placement you will get an array of length n where this is not empty, every element is filled. So then you can compute this number b1, b2, b3 and b4. So they should be strictly increasing order. So your goal is to find out in how many ways can you place elements from 1 to n such that the sliding window maxima is strictly increasing. And that is the entire problem statement. So just a single line problem statement, but it will teach you a lot about combinatorics, competitive programming, and most important, observation skills and how to approach vague problem in Codeforces, Codechef, and in general any competitive programming website. So now let's talk about how you would attempt it as a beginner in the contest, because right now with this setting it is completely vague. You don't have any idea what exactly to do, right? You just know that there are a bunch of sliding windows here and there, and you have to ensure that their maxima is strictly increasing order. But then you can notice that there are multiple ways to place elements from 1 to n. So there could be multiple different maxima. How do you coordinate all of these, right? How do you ensure a dependency between them? So to do that, my first advice to you is you always start small. That is, in this kind of problem where everything looks vague, you have to have the oversight of starting with something that is familiar to you and that you could easily analyze. But what exactly should you start with? Like when I say start small, what does start small actually mean? So if you have seen my earlier Brain Gym series videos, I have talked about this concept, especially in ad hoc problems. For example, if you remember, there was a problem where you were only allowed to swap even and odd elements, something like that. And in that setting also, the problem statement was too vague, and we said that okay, better to just focus on 2 elements at a time instead of focusing on a big subarray. So this starting small, so this comes from experience. And then the first observation that I'm going to make right now, this is something that comes from my intuition. Okay, so this came from my intuition, and but how exactly did I build this intuition? That came from experience, I would say. So this intuition came from experience. And right now, as you are watching this video, you are gaining that experience part. As to the intuition part, you will eventually develop it as long as you keep on solving more problems. And the first observation is that this is the major hint. And keep in mind that as every time we make one observation, we take some points of the difficulty rating of the problem, because once you know that this is the direction to take, or once you have made some observation, you will reduce the difficulty of the problem. So our goal is to make this problem easier and easier until it boils down to a state that we are completely familiar with. And this observation is that you have to focus on maxima. Focus on maximum element of the entire array. So focus on the maximum element of entire array. Now for some of you, this might seem entirely out of the blue, like how come we suddenly started thinking of the maximum element of the entire array? But this is in fact a very standard technique in competitive programming, especially when you are dealing with these subarray maxima thing. So most of the time you can actually make some very good arguments about the maximum element and the minimum element. For example, if you have seen certain problems that ask you to change some element, increase some elements, decrease some elements, and so on. In these kind of problems, it is very useful to focus on one particular element, which is the minima and the maxima. In fact, if you remember, I recently uploaded a brain gym series video called ad hoc problem final boss, wherein wherein the key insight was focusing on the path that the minima was taking, because minima could not increase, so that is why we were focusing on minima there, and hence we have to focus on the maximum over here. Now I'll give you some more intuition about how I suddenly started thinking about the maximum element of this entire array. Because if you notice that there are several windows, you have this window, this window, this window, and this window. One good thing about the maxima, let me first of all remove all the clutter. So one good thing about the maxima is, suppose the maxima is present in this yellow window. So maxima resides in the yellow window. Then one thing you can say for sure, that in this yellow window, the subarray maxima will be the maxima of this entire array, because no element is greater than it. Let's call it as m. But another quick thing that you can notice is that this sliding window maxima has to be strictly increasing. This means that once you move out of this yellow element, then you will start having problems. Why? Because you just lost a maxima. Or if you didn't lose the maxima, then uh, maybe you gained another copy of a maxima over here. That could also be a possibility. But still, it is worth analyzing what happens to the maxima. And this is where the intuition for focusing on the maximum element came from. Now, a lot of people, a very common mistake that beginners make with this approach is, when focusing on a maxima, they forget about the duplicates. That is, maxima could be present at multiple locations. So we have to keep this fact in mind while solving the problem. Now, with this in mind, now we know that we have to focus on where the maximum element could be present, and then we have to make some observations on it. So how do we make those observations? Now let's look at this window again. Let's look at the figure on your screen, and also let's keep in mind that maxima can have multiple copies lying in several windows. Okay. Now let's see. We want to find out. This is our goal. Which window can contain which window can contain the array maxima m. Array maxima m. Suppose m is the maximum element of the entire array and we have to find out where can it be possibly located, right? This is what we are trying to investigate. Now let's start with this blue window first. Can it be present in this blue window? And here is the point where you have to keep your eyes and your brain open and you have to think very carefully before you answer. So assume that the maxima is indeed present in this blue window. Then in the next window that you are creating, which is this green window, you are transitioning from this blue window to this green window. So what could happen? So if you have the maxima m over here in this blue window, then how did you create this green window? You took this blue window over here, this big window that you see over here. You removed one copy of the maxima. Sorry, you removed one element and you inserted one element to get the next window. Now assume that you removed maxima. If you removed maxima from your window, this means that since maxima is no longer over here in this green window, then whatever the maxima of this green window, that will be strictly less than this blue. So you can clearly see that the maxima of the green, right, this will become strictly less than maxima of the blue element. Why? Because the maximum element was only present over here. So whatever element is present over here, since you lost the maxima, you lost the battle, and that's why maximum element, if you lose the maximum element, it's not good. But now what about the other case where you don't lose the maximum element? That is, here suppose you lost the maximum element, or let's consider another two cases at once. That is, maxima resides over here or maybe also resides over here in between. And if it resides over here, then once this element is cut off, you added one element, assume that you added one copy of maxima back. Now in this case, you didn't lose the maxima. But now notice that since you didn't lose the maxima of this green element is still m. But here is the part where if you are paying close attention to the problem statement, you will realize that the problem says that it has to be strictly increasing. So actually it doesn't really matter whether you lose the maxima or you don't lose the maxima. Both the cases are bad, right? Both are bad. This means that blue element, the maxima cannot be in the blue region. That is for sure. So now we have to find out where can the maxima actually be. So it can't be in this blue region. That is for sure. So this blue region is out of the game. Then with that same argument, you can say that it also can't be in this green region. Why? Because this green region and this yellow region will compete, and either you lose the maxima or you don't lose, in which case you are not making it as strictly increasing. So this also cannot be in maxima, also cannot be in the green region. Same for this, maxima also cannot be in the yellow region, because then yellow region and white region will lose the battle. So now you come to the very important conclusion that the maxima has to be in the last window only. So now let us write down the observation that we have just made. Maxima or let's say array maxima. array maxima can only be in the last window. It can only be in the last window. In the last window. So this is observation 2. Observation 1 was getting the intuition. This is observation 2. Observation 1 was getting the intuition that you had to track the maximum element of the array along with the duplicates. And observation 2 is that the maxima has to reside in the white window. Why? Because if there is a window that is competing after it, like so, then this cannot increase the maxima. It can either maintain it or it can decrease it, and both the cases are bad for us. So that is why it has to be in the last window only. It can have multiple copies in the last window and it can appear anywhere in this last window. So now let us focus on finding out, okay, now that we know this fact that maxima only resides in the last window, but where exactly in the last window and how many copies are allowed, right? How many copies are allowed? Now, if you pay very close attention to what I have just written on the screen, the statement says that array maxima can only be in the last window. This means that it can only be in the white region that you see on this screen over here, right? But now notice that it cannot be here, it cannot be here, and this requires, I would say, some sharp observation skill. It is not obvious why it cannot be here and here. And I wouldn't say very sharp because in one way it's very obvious just by looking at the fact that it's written on the screen. But if you stop to think about it, maybe it's not that obvious to some of you. So the fact is, this statement says that the maxima can only be in the last window. Now assume that you placed a maxima over here, this second last element, right? And actually let me clear the board a bit so that it doesn't get very confusing for you. So we have, this is the first window, this is the second window, third window, and finally this is the last window. Now we want to find out, can the maxima be here, here, or here, because we know it has to be in one of these. Now notice what happens if you place a maxima over here. If you place a maxima over here, then using a very interesting property of maxima, that if you have the subarray, if you have the array maxima, and if this array maxima competes with any subarray, it will win. That is, it will always, array maxima remains a maxima of a subarray as well. So this fact might seem very obvious, that array maxima will remain a maxima no matter how small of a subarray you create. But this is actually very crucial to proving why this maxima cannot be here or it cannot be here as well. And the proof is that, suppose this maxima was indeed present over here, then notice that this maxima is now included in this yellow window as well. This means that this statement has now become wrong, because this statement said that the array maxima should only be present in the last window, and this means that there should be no overlap. That is, array maxima cannot be in an element that overlaps two window. And why is this true? Because if it overlaps this, suppose the array maxima is present over here, array maxima is present in this overlapping element over here. So if it is present in overlapping element, then it will be the maximum element of this window as well and this window. So this means that now we have made a very important discovery about the maximum element of this entire array. And what is that discovery? let's formalize it. So you can notice that we can now claim that the array maxima has to be at the last element only. This is where your maximum element should reside, only in the last slot. And all of this we arrived after making a series of observation. But if you now stop to think about it, this is actually very easy to like infer if you had come at it from a different direction. Because let's say if the array, you can make some arguments like so. Assume that array maximum is over here. If the array maximum is over here, it means that there is a window ending over here, and then there is, you can slide this window and you can create an array, you can create a window ending over here. So now since you have two windows ending, one ending at the maxima and one ending at the element immediately after the maxima, then it means that both of these sliding windows have the same maximum, or the second window has a smaller maximum, right? So if this is m, it will be something smaller than m. This means that this condition will be violated, and that is why it is very important for you to place the maximum at the last element. So this looks very easy to make this argument, but that depends on like whether you see, because if I started the video saying that okay, my claim is that maxima cannot be an internal element, and then I try to prove my claim, then again you might wonder that how come you even thought about this claim. So these are the things that is going off the top of my head, that okay, I need to process all of these windows. Then I got the hint that okay, I have to think about the maxima and then slide the window forward and then see which overlapping elements can the maxima be in. But once I have reached a conclusion, then it is very easy to verify that conclusion without using such complicated logic that we have just used. And you can make very simple arguments saying that if the maxima is an internal element, then just consider the sliding window that ends here and the sliding window that ends here, because there is definitely a sliding window that ends here and there is definitely a sliding window that ends over here. So with that said, we know that the maximum element can only go over here. Now what is the next hint that we can observe? Like, let's make some more observation. So once you get to know some interesting facts about the maximum element, of course the natural instinct is to start thinking about where you can place the second maximum element, right? Where can the second maxima be? Again, let's follow that same trick. You have this window, and then you have the next window, and the next window, and the last window. Now this spot is reserved for maxima. That part we acknowledge, that's fine. But what are the spots for the second maxima? Now notice that maxima is reserved over here, and also another fact that you can notice, that there can be no duplicates, because I had mentioned earlier that in these kind of problems people usually forget to account for duplicates, and that creates some corner cases. But then we have just proved that there cannot be two copies of the maxima. The maxima, we said that it has to be only in the last window, it cannot be in an overlapping region, and that is why maxima has to be in the last slot only being the driving factor over here. This means that maximum element should not have the duplicate. So if the maxima does not have the duplicate, this means that there is nobody competing with second maxima wherever it is, unless second maxima is in the last window itself. So let's again analyze it case by case. Can the second maxima be present in the blue slot? So you can see that since maxima is not competing anymore, then that same arguments that we made for the maxima, that is when you convert from this blue window to this green window by sliding one element, then you would either lose the maxima and you go to m dash which is less than m, or let's say sm means second maxima, or you retain the second maxima by getting additional copy of the element that you just lost, or let's say the second maxima is an internal element. In either case, you can see that either your second maxima is retained or it becomes smaller, and both of them are bad for us. Why? Because second maxima, if the second maxima is in the blue region, that it has to be the maxima of the blue region. Why? Because because the maximum element is not competing anymore, it is silently sitting at the end. And using this argument, you can now say that second maxima cannot be in a window after which a window starts. Why? Because if if two win if second maxima is over here and after this a window starts, then both of them will not satisfy this strictly increasing behavior, because second maxima is as good as maxima of this entire array, because the maxima is not participating anymore. So this means that second maxima has to be in the last window only. And this is also another important but non-trivial observation that we have made. So you can see that second maxima can only be in this region, this red region. But you know that this last spot is reserved for the maxima. So this second maxima can only be in this part or this part. And again, if you are observing clearly, if you were observing closely, you would notice that the important keyword is that only, that is second maxima can only appear in the last window. This means that it cannot be in an overlapping region. That is, any element which has two colors, the second maxima cannot be there, except this red one, except this red one, because in the red one the maxima is the green element. So you can think of this red window is non-existent, because if you place a second maxima over here, then you see that nobody competes with it, because after this no window starts. But if you place a second maxima over here, you will see that it can create issues, because let's assume that you place a second maxima in this overlapping region which has two colors apart from red, right? Now what will happen if you place a second maxima over here and the last element is over here? Then you can see that there is one window that includes the second maxima, which is this green one, sorry, which is this yellow one. Yellow window includes the second maxima, but the green window also includes the second maxima. This means that the second maxima also cannot be in an overlapping region. And by overlapping, we mean overlapping except the last window, right? Because this last window is as good as non-existent, because that anyway the maximum of that is the red element. So second maxima cannot be in the overlapping region. So with this, you can see that we have now proven that the second maxima of the array has to be over here. This is the, if this is the max, this is the second max. Then you can make this same observation again with this window technique, and then you will realize that this pattern actually holds for more windows as well. That is, the third maxima has to be over here. And this time you don't need complicated proofs, because if the third maxima is not here, then it means it is here, or it is on the left hand side. But if it is here, if the third maxima is here, and we know that second maxima cannot have two copies, it cannot have duplicates, because we said that it can only appear in the last window, and even in the last window there was only one slot for it. So this means if the third maxima is over here, then third maxima will win in this yellow region, and it will also win in the green region when you compare with the when you figure out the maxima. So this means third maxima only has one possible slot, which is this one. So this means that we have now made a very, very crucial breakthrough, which is that looks like the trend is continuing. So maximum element goes here, second maximum element goes here, third maximum element goes here, fourth maximum goes here, fifth maximum goes here, sixth maximum goes here. So is it the case that we have to just construct sorted array and print the answer? Like and if that is the case, then we know that there is only one sorted array that contains integers from 1 to n. So what is the catch? Is the answer actually 1 for this complicated problem, or is there any catch? So yes, there is a catch, because you will notice that all the arguments that we have made so far, they will remain valid as long as we can make this window moving argument. That is, this is one window, and then there is a window that starts after it, and then you claim that okay, you cannot place an element in this overlapping region because it will be the maxima in both of these elements. So you can already see that some of the elements would be special, because at at those elements a window will not be ending, because you see that a window was ending over here, window was ending over here, window was ending over here, window was ending over here. But for these two elements, no window was ending over here, because if you see, this is the actual window, first window, and second window, third window, and fourth window. So you can see that these two elements, they are special. In fact, not just for this problem, since we are here to learn general techniques about sliding window, you can always say that in any problem that deals with sliding window of length k, the first k elements would be special. So let's locate the or let's say the first k minus 1 elements. So this element and this element is special because nothing ends over here, and after this something ends over here for sure. Something ends over here, and then something ends over here, and then something ends over here, and something ends over here. So you can see that it already divides the entire indices into two area. One is the special one, and one is the non-special ones, where uh, something ends, right? Now let's see how far our arguments are valid. So whatever argument that we have made, assume that we know that maxima can only be placed over here, and this argument was made because if maxima is we made this counter claim that if maxima is indeed over here, then consider the window ending over here and consider the window ending over here. Both of them have the same maxima, which is not possible, right? So this means that if you want to make the claim for this second maxima, right, like let's say if this is m1 and if you want to make the claim for m2, then you can use the same argument that consider the window ending over here and consider the window here the claim that you want to make is that m2 cannot be over here, and your arguments are this, that consider the window this one and consider this window. Both of these have maxima as m2, so that is wrong. So that is why you have to place m2 over here. So that's fine. M2 goes over here. M2 means second maxima. Then let's say for M3 you want to make a claim that M3 can only be over here. So let's see if that claim is valid. So suppose if you place M3, then you can make that argument that this window has maxima as M3, but this window also has the maxima as M3. Why? Because M2 is out of the game, M1 is out of the game. So in both of these window, either M3 will win or it will lose. Both of them are bad for us. So now you can confidently say that M3 is for sure, M3 for sure will stay over here. And now we are coming to this index. Now let's focus on this index. Now what about M4, right? Can we make that same argument that M4 has to live over here? So if you want to make this argument that M4 has to live over here, then you have to again do something like this. You claim that, okay, assume that M4 lives over here, and then you show me that M4 is present in two windows. But now you can see that M4 cannot be present in two windows, because suppose if M4 is present over here, so in this window M4 will win, but in the next window M3 is there competing with it, so M4 will not win. So this means that this set of special indices are not just this. It is actually, we thought it is the first k minus 1 element, but actually the first k elements are special, because first k elements have a lot of freedom to place their maxima, but the remaining n minus k elements, they are bounded to place their maxima in decreasing order. So now we have made another breakthrough, that is, given any array, so you can see that these three blue elements form the first three elements form the blue block, right? This is the first three element, and if you remember, we were solving it for n is equal to 6 and k is equal to 3. So you can see that given an array, you can first of all partition the first four elements into one region. Let's say that this is one region, and the remaining n minus k elements in the other region. And you can see that this other region, this is very constrained, because this is very constrained, and this is sort of free. Why constrained? Because this green has to be sorted. This green region has to be sorted. Green has to be sorted. Not just that, we have made some more interesting observation, which is the fact that M1 resides over here, M2 resides over here, M3 resides over here. This means that nothing bigger than M3 should reside in this free region. Because if you have already placed the first maxima, second maxima, third maxima, and you know that there cannot be duplicates of the third maxima, nor can there be duplicates of the second maxima or the first maxima. This means that in this blue region, everything, so you can make this bold claim that blue, all the elements of the blue region, they are strictly less than M3. M3 is the third maxima. This is one bold claim and observation that you can make, that the blue region is strictly less than M3, and another bold claim is that this green region has to be sorted in strictly increasing order. And you can see that these conditions are not just necessary, because we have made some necessary constraints, right? But you will see that these are not necessary but also sufficient. And why is it sufficient? It is sufficient because if you follow this reasoning, why is it necessary? Because we saw that there is no option than to place M1 over here. There is no option other than to place M2 over here. There is no option other than to place M3 over here. So that is why it is necessary. But why is it sufficient? Like, why does placing this guarantee this? And this is where the next phase of this video comes in. And I told you earlier, right, that I would show you a way on how advanced level coders think about these problems and why they do not have to do such case analysis that we have done so far. And in fact, if you read the editorial will start with this. Most probably it will start with this advanced segment saying that it is obvious to see that xyz happens, and then they'll prove something. Or they will mention that okay, it can be proven or it can be shown that this fact happens if and only if that fact happens. So I'll show you how you can make the same argument in a very concise and precise fashion, and that will also prove the sufficiency. So we got off track a bit because we started focusing on the maximum element of the array, and we tried to find out where it could be located, and which is a good deal, like which is a good deal because it eventually helped us uncover a lot of techniques to solve this problem. And in fact, this is the one thing that is recommended to beginners, that you start small, focus on the maximum element, and you'll get there. But again, these rules do not apply to intermediate or advanced level coder, and I'll show you why. So we can make this same observation that we have just made, that m1 has to go here, m2 has to go here, m3 has to go here, and these elements have to be free. We can make this same observation in just 1 to 2 minutes with very perfect arguments, and the argument goes like this. And this is where some sharp observation skills and experience and intuition is required. So the arguments goes like this. So let's consider the first window. So this is the first window of length k. Then it will have a maxima. I don't care whether it is the first maxima, second maxima, third maxima, or whatever. It will have a maxima. Let us call it as b1. Then let us consider the second window. In this second window, either this maxima is retained, which is bad for us. This means so two things can happen. Three things can happen actually. Either this b1 is retained, or something bigger than b1 comes up, or something smaller than b1 emerges as the maxima. So suppose this outgoing element is b1 and nothing bigger than b1 has emerged, then b1 is no longer the maxima and the maxima is smaller than b1. Or suppose that the b1 is lying over here and overlapping region, then b1 will be retained. Or suppose that the incoming element is bigger than b1, then it will act as the new maxima. So you can see that since you have to make the sliding window maxima in increasing order, then b1, no matter where b1 is located, actually in the first window you can see that it doesn't matter where b1 is located, the incoming element has to be bigger than b1. And just this one line proves that the first k elements are special, and in the first k element it doesn't matter where b1 is included, the incoming element has to be b2 and it has to be strictly greater than b1. This means that whatever maxima this has to be, whatever the maxima of this first window is, suppose that is b1, incoming element has to be greater than that maxima, because if it is not greater, then it means that either b1 wins, which is bad, or b1 doesn't win and something smaller wins, which is also bad. This means that this incoming element has to be greater than b2. But then once b2 has entered this window, you can completely forget about this first window, and then you can apply the recursive argument, that is, consider this window and we know that the maxima is at the terminal position. Then what about this window that will emerge next, this window? Then you can make the same argument that this incoming element has to be bigger than this element, that is, this has to be greater than b3. B3 has to be greater than b2, and then you can follow this chain, and you can see that with just 2 to 3 lines of reasoning we were able to prove that whatever happens in the first window doesn't matter. B1 can be hidden anywhere, but the incoming element has to win. So this has to be strictly greater. So if this maxima is like, let's say x, then this has to be greater than x. And let's say this is b2, then this incoming element has to be greater than b2, which is b3, and this has to be greater than b3, which is b4. And with this, now you can see the powerful way of flipping the perspective, I would say, because previously we were focusing on one small thing, which is what is usually taught to us. But then this time we actually started doing multiple things at once, and it's actually counterintuitive how this approach is so much easier to think about, to reason about, to come to conclusion. But maybe not that intuitive, I would say. uh, I guess, yeah, I mean, it all depends upon your experience, how experienced you are. I mean, if you are an experienced coder, you could have definitely made this argument that consider this first window and let's figure out what happens to the maxima of this window when this window slides forwards. So anyway, I hope at least you learned this trick from this video, that instead of thinking about the maxima, sometimes it might make sense to think about a general maxima and then slide this window, then track what happens to the quantity that you are trying to track, which is the maximum element of the window. So now with all of these observation skills in place, now let us see how we can solve this problem. So we know for sure that the first window is special, and another fact that we know, if the maxima of the first element is x, then the rest of the elements should be strictly greater than x, and not just that, they should also be in sorted order. Then you can see that if you draw the numbers on a number line, if this is 1 and this is n, and suppose x is located over here. So we don't know, since we have to place numbers from 1 to n and nothing is placed yet, then we don't know what is the maxima of the first window, because we know that this first window, all the elements of the first window are special. So we don't know what is the maxima of the first window. So what can we do? We can say that, okay, we are not aware of the maximum of the first window, but all possibilities can be considered by varying x from 1 to n, because x could be any number between 1 to n. So why don't we fix the maxima and find out the answer? And this technique that you just saw, that I just did, is known as the contribution technique, wherein you try to find the contribution when a particular quantity is fixed. So this is also used in let's say counting inversion problems, where you try to fix an endpoint j and you try to find out the maximum sum sub array ending at j, right? So that is also DP, but that is also contribution technique. So a lot of overlapping things. So here also we'll kind of do the same thing. Since we don't know what is the maximum element in this first special window, which is of size k, then let's assume that x is any number between 1 to n, and for each x sum up all the values, that we wouldn't miss anything. So suppose you partition your number line at this partition point x, then you know that on the left hand side you have to arrange elements such that you are only allowed to use elements 1 to x. Why? Because their maximum is x, so you cannot use elements from the right region. But at the same time, you have to also ensure that the maximum x is actually achieved. So this is one problem that we will solve independently. But first, let's talk about the right hand side. On the right hand side, you can see that you have how many elements remaining. So since the first window is special, first window contains k element. On the right hand side, you have what? N minus k elements. So for these n minus k elements, you want to place some elements over here, and they should be in sorted order. So how many choices are there? So since you have used up x elements on the left hand side, you are only allowed n minus x choices. So if you are only allowed n minus x choices, and suppose this n minus, so there are 3 slots over here, but then n could be big, and like let's say if n is 3, then there could be more than like suppose you want to restrict x as let's say 2, then you have 4 numbers remaining, but you only want to use 3 numbers over here. So this means that you have n minus x choices to pick from, but only these many slots to fill. So the number of ways would be simply n minus x choices. Out of this, you only choose n minus k numbers. And once you have chosen the number, now notice a clever observation is that you don't actually need to permute them, because choosing a subset is actually equal to choosing in a sorted order. This might not be obvious to some of you, like how come we are just choosing a random object and then we are not worrying about the sorting. And this is also a common trick in competitive programming, that whenever a problem talks about a subsequence but doesn't really use the property of a subsequence, then you can treat it as a subset. And if a problem talks about a subset, and then if you want an ordering of the subset, but then the ordering is uniquely defined given a subset. So for example, if I give you a subset of like let's say 2, 1, 3 and 1, then it has a unique sorted order 1, 1, 2, 3. So since this ordering is uniquely defined, then just selecting a subset is actually equal to selecting and then sorting. So this means that there are this many ways to select uh, elements on the right hand side, right? You can in this many way you can place all the non-special elements, right? There are n minus x choices available to you, and from that you have to fill n minus k boxes. So you can do that in this way. Now the interesting part is with the special element. So how do we solve for the special elements case? So for the special element, and this is where the Codechef problem from the last starters contest would come in helpful. And in the last starters, it was asked to find the LCM, find the number of pairs that achieve LCM is equal to L, right? In that video, somebody had made a YouTube comment saying that it could be solved via a simpler way using combinatorics. And I had also linked a different practice problem on my YouTube channel that used to solve a general problem. And that general problem is how many arrays of length n exist such that their LCM is equal to L. And in this problem, I had introduced a combinatorics technique that is widely used in competitive programming, which is called inclusion exclusion. And we can use that same technique to find out the answer for the left part. So now notice what the left part needs us to fill. So if this is your partition point x, if this is n, and if this is 1 and this is n, we know that the numbers on the right hand side can only come from this right region, right, from x to n, right, and the numbers from the left region, it can only come from this region from 1 to x. Actually here I should have since we are saying that the maxima for the left region is x, then the right region has to start at x plus 1, right? So whatever formula that I showed you on my screen, that was maybe not correct. It should have been n minus x plus 1, but anyway, that doesn't matter. I mean, what matters is that you know what we are trying to accomplish, because I will anyway show you the correct code at the end of this video. But yeah, the point that I was trying to make is that uh, actually, that formula was my bad. Actually, that formula was indeed correct. It was indeed correct. I just realized, because if you can only select numbers from 1 to x, you have x choices. But then if you can only select number from x plus 1 to n, you actually have n minus x choices, which is what we actually used as the formula in the previous slides that you saw. So that formula is actually correct, because in this region excluding x, there are actually n minus x numbers, and that is why n minus x plus x equals n, because if this region has x numbers, then this region must have n minus x numbers. So okay, got sidetracked a bit, but okay, back on track here. So now the problem that we are trying to solve is that place numbers from 1 to x on the left region such that their maxima is equal to x. So the first solution that comes to mind is that, okay, in the first region is special because everything could be, anything could be the maxima. There could be multiple copies of the maxima. uh, no restrictions at all, right? That is why it was considered as special, because the sliding window argument did not hold, because there was no sliding window to the left of it, and that is why the arguments did not hold. So the first solution that comes to mind is that for the first element, how many choices that you have? You can place any elements from 1 to x. So you have x choices. For the second element, you have x choices. For the third element, you have x choices, and so on. So you have a total of x to the power k choices. Why? Because the first window is of length k. So at first glance, it looks like this should be your answer, right, for placing the elements on the left hand side such that the maxima is x. Why? Because we have not used any elements from the right hand side. And then for each x we can sum up this quantity. So if the answer, if the ways of placing the elements on the left hand side is x to the power k, and the ways to place the elements on the right hand side is n minus x, choose n minus k, then we can simply sum it up from x is equal to 1 to n. And this should be our final answer. Why? Because the left part and the right part are independent. The only dependent part was this partition point x, and that has already been covered when selecting the choices. But now if you use this formula, you will realize that you might end up over counting. Why is that? Because when you chose this partition point as, like, let's say 3, then there is a configuration in which all the elements are, like, let's say 1 2 2 1 1. Nothing achieved 3. And when you actually counted this x is equal to 2, even in that case, this same configuration can happen, because the maximum is 2 and somebody achieved 2. So in both of these cases the left half looks equal, and in both of these cases the right half will try to make some choices, and let's say the right half contains only one element, it contains n. So in both of these cases it will contain n. So you see that you just double counted this configuration in x is equal to 3 as well as x is equal to 2. This means the thing that we are doing wrong is that we are not ensuring that this maxima has actually be achieved. So that is why this is not disjoint, and this is one important thing that you have to take care in competitive programming, that whenever you are trying to make a choice, when you are solving in contribution technique problems, you have to make a choice and you have to make sure that they are not just disjoint but also exhaustive. That is, they should cover all possible possibilities. So it is exhaustive for sure. Why? Because we are iterating x from 1 to n. So we can say that it is exhaustive. But it is actually not disjoint because your duplicates are appearing. So how do we make it disjoint? To make it disjoint, you can say that whenever you are doing a partition point on x, then every array in x is equal to 3 will differ from x is equal to 2. If you can make this guarantee, then you can say that you have now split it into disjoint set. And how do you ensure this guarantee? You can ensure this guarantee by saying that whenever you are deciding a partition point, you say that this maxima is not just, these elements are not just sampled from 1 to x, they are sampled in such a way that the maxima has actually been achieved at least once. There could be multiple cases where the maxima has been achieved, but there should be at least one occurrence. So if you have this definition, that is, don't just sample from 1 to x but also sample in such a way that you achieve the maxima at least once, then you see that the x is equal to 3 and x is equal to 2, all the arrays that it creates, the left half will always be different. Why? Because the left half in each of this configuration, the left half will have the maxima 2, and in each of these configuration the left half will have the maxima 3. So of course these two arrays are different. So then the problem is, how do you count the number of ways to achieve how do you count the number of ways to sample integers from 1 to x such that you achieve this maxima x? And now this is where things get a little bit tricky if you're not familiar with the right techniques, because you might try to think, okay, let me try to assign x first, and then for the remaining thing I can do x to the power k minus 1, right? This is actually incorrect. Why? Because this is just x to the power k. So of course this is incorrect, because just assigning to 1 doesn't really, sorry, I mean, I wanted to say something like this. Let's say you do 1 into x to the power k minus 1. Like you think that, okay, I will pick one element, assign it as x, and then the remaining element will go to x to the power k minus 1, because once maxima has been achieved, every element has freedom. So this looks correct at first glance, but this is actually incorrect. Then again you might try to fix it by saying that, okay, I actually can pick any of these elements as my choice for fixing this x, and then you can say that, okay, there are k choices to fix the element that you want to assign as x, and then for the remaining elements you can do x to the power k minus 1. So you think that this is the correct answer to this problem, but actually there is a serious flaw in this. Maybe try to pause this video and try to figure out why this formula is not correct. And this is not correct, it's because this time you made the right insight into observing that actually uh, maxima could be as well here, as well here, as well here. But now notice that if you fix maxima as x over here, and then you allow every element to vary freely, that is why you added this x to the power k minus 1, then there will be a case where this becomes x. But then in the other iteration, when you fix this element as x and you allow all the other elements to vary freely, there will be a case where this element becomes x, and then you see that this and these two elements become equal, and there will indeed be a configuration where this section is same for both of them. So you ended up overcounting. So that is why all of these tricks, these look like they would work in theory, but it actually does not work. So this is a very standard problem in competitive programming, that if you want to distribute elements from 1 to x to k elements such that you want to achieve x at least once, then the trick is to use the principle of inclusion and exclusion. And what you do is you say that, okay, how wrong can I be if I just blindly assign everything uh, in 1 to x? So it has x choices, x choices, x choices, and so on. So the total number of ways is x to the power k. But there are some bad actors over here. There are bad arrays in which the maxima is not reached. But can you actually locate out how many bad elements are there in this configuration? So yes, actually you can figure out, because if you see that if you use x at least once, then you are good, because your maxima will be equal to x. This means that the bad actors, the bad arrays, the bad configurations are nothing but where you did not use the maxima at all. This means I told you to sample from 1 to x, but you didn't even use x. So this means you indirectly sampled from 1 to x minus 1 without any restrictions. And in fact, all of these samplings, this sampling, the sampling from 1 to x minus 1 to x minus 1, this sampling is a proper subset of this sampling. This sampling 1 to x minus 1 is a proper subset of 1 to x sampling. Why? Because you can completely ignore x. This means all of these samples are actually present over here as well. You have already counted them, and in fact there is no other configuration that you are missing, because all the other configuration, they use x at least once in their sample. So this means if you can just subtract this x to the power k, if you remove the bad actors, which is x minus 1 to the power k, this gives you exactly the number of configuration where the maxima is achieved. And this is the trick that we had used in LCM based problems, because in LCM based problems also you have to achieve the maximum of a1, a2, a3, a4 is equal to the exponent of the prime factor. So it has to be equal. So this means maxima has to be reached, and this trick is very common in LCM based problems. So that is the final trick. that I wanted to show you. So then combining all of this fact, you can now see that the answer is simply the summation of this quantity. That is, you fix a partition point x, and this partition point will denote what is the maxima of the left segment, which is the special half, and then you multiply the number of ways to color the rest left segment, or basically the first special segment. That is nothing but x to the power k minus x minus 1 to the power k into how many ways are there to distribute the right segment. There are total n minus x elements still remaining and n minus k slots still remaining. So this is the final answer to this problem, and this can be actually computed in O of log n, and this is actually a good exercise for you to learn how to use Atcoder's library to compute fast powers. And this combinatrix, or this combinatrix, yeah, this can be calculated using factorial, because this is nothing but n factorial by r factorial into n minus r factorial, NCR. And factorials can be pre-computed also using Atcoder's library, which I will show you right now in the code part. So the code part is very easy to implement, but if you do not know about mod int library from Atcoder, it is a good problem to get your libraries in place and learn about mod int. But other than that, now you can see how just some series of observations led us to solve this very complicated problem in a very simple manner, while also learning this fancy trick of principle of inclusion exclusion, and also learning the fancy trick that sometimes whatever everyone tells you that you have to start from the smallest element might not always be the correct idea if you are not really a beginner in competitive programming. So finally, let's look at the code for this problem. So first you write the code for computing the factorial. That is very simple. I am using a data structure called modin, and by the way, it is 2026. You shouldn't be doing any modular stuff yourself or fast power stuff yourself, right? At Coder library exists, go ahead and use it. So with this, you don't have to worry about overflows and whatnot. So I just pre-computed all the factorials up to 10 to the power 6 so that I can reuse it across test cases. This is pretty simple. And then n choose r is basically n factorial by n minus r factorial into r factorial. And if either is less than 0 or greater than n, I simply return it as 0. Then I told you that you have to split it into two segments, right? One is the special part, which is the first window of size k. And now it looks very obvious why it is special, right? But if at the start of this video I told you that this part would be special, then it wouldn't have been obvious, right? So this is special part. Like if I told you that this partition point is x, that is you want to place n elements, or basically k elements, such that their maximum is x. Then the number of ways is equal to x to the power n minus x minus 1 to the power n, right? So this is the number of ways to place the left part, and the number of ways to place the right part, which is the place RHS, is nothing but the number of choices that you have, which is nothing but n minus x, and the number of slots that you have. So the slots would be n minus k. So since I was writing a general function, I added it as n so that it is easy to code. And this you can view in isolation, because this trick you can actually use in future problems as well. And finally, for the final solution, you see that it's just a bunch of lines of codes wherein you start with this array and you start with this number line. This is 1, this is n. You find out your partition point. Your partition point could be any number between 1 to n, and if you want to make it exhaustive and also disjoint, then you have to enforce a maxima on the left hand side, and you can enforce a maxima using this place LHS function that we just described. And in the LHS you have k elements that you want to sample from, and the sampling should be done from 1 to x, while also ensuring that the x is achieved. And on the right hand side you want to sample from n minus x elements, but after you have done the sampling you have to sort it, and that's why there is only one way to sort it. So that's why all you have to do is sample n minus k elements from n minus x element. And since both the choices are independent, right? Why are both of them independent? Because no matter what the maxima is, because the maxima will always be x, because so no matter what the configuration is, the right hand side could start at 259, this is a valid configuration, but it could also start at 1723, this is also a valid configuration. So all of these valid configuration can be tied up with any valid configuration from the left half, because left half is not interacting with the right half. Why is it not interacting? Because of this unique partition point trick that we had introduced. So this partition point introduced, this ensures that this left half and the right half becomes independent. So that's why we multiply LHS with RHS and print the answer. So as you can see that the code is super simple for this complicated problem, but the observation skills and the ideas involved to solve those problems were very powerful. And I think this is what is needed in today's age of competitive programming to succeed. So let me know if you had any other intuitive way to arrive at the solution, or any other fancy way that you would like to share with others. Do let us know in the comment section. And yes, the I will also link down the problem in the YouTube description, and also the other problem that I was talking about that uses this trick for LCM. I will also link that down in the YouTube description so that you can go and solve that. So yeah, that's all for today. Let me know how you found the flow of this video, because this was kind of an experimental video, because in a lot of my videos I also use the text box to write out a bunch of stuff. So I don't know which one is more helpful. Just using the pencil and then writing in that same flow is kind of easier for me, but might make the video a bit more long, I would say, for you. And maybe my writing might not be good, so it might not really be clearly legible. So do let me know your feedback in the comment section. Which format do you like best? Do you like the format where we just start with the pen and then we keep on drawing stuff and so on, or do you want me to pause in between and then create text boxes and write? Because actually it's not easy to switch between keyboard and whiteboard that I have, writing pad that I have. So but still, I wanted to know your opinion. If you still think that using keyboard is actually better at some locations, because whatever I write with pencil I will usually delete it sooner or later, but with keyboard whatever I write it will be on the screen for a bit longer time. So depends upon how you are actually consuming the content. So do let me know in the comment section. That's all for today. Thank you.